let's look at Amidons information from iron powder and ferrite coil forms on the exact procedure for winding a toroid inductor from calculations. Firstly, we need to know the inductance. And for a certain purpose, I need 15 microhenry. This is a power application, 1250 volts peak, a lot of voltage. So this is a serious problem. If I get the wrong core, it'll burn up. So for this purpose, I'll use a material number 2 there at the top of the column. Mu is 10, 1 to 30 megahertz, be operating at 3.8 megahertz. And I just happen to have a core that is a 1.30 T-130 under the physical dimensions on page 3, top of the right-hand column. T-130, outer diameter 1.3, and we go over to the cross-sectional area in centimeters squared, and we write down 0.73. Now we need to go down to the A sub L value for that core and that material. Left-hand column, core size, which is T130. And across the top, we see in the middle 2 mix red. So we go to where the row and the column cross. Pardon me. T130 and 2 mix red, and that gives an A sub L of 110. We write that down. Now we go up here to this formula for the approximate number of turns for the inductance and A sub L, and we do the turns formula. We do desired L in microhenry, 15 microhenry, divided by the A sub L value we just looked up of 110. We take the square root of that, multiply it by 100, and the result is about 37 turns. That's a lot of turns on a small core, but there are benefits to having more turns and a less permeability core, because that puts some of the heating losses in the wire, which is external. Now the big question, will the core burn up? In this case, yes, it will become smoking, flaming disaster. But we go down here to page 10. Under power considerations, iron powder and ferrite, we see this list of frequency and AC flux density, and between 1 and 7 megahertz, we're kind of guessing a maximum of maybe 100 Gauss. So we go down to this formula for B sub max. We see E peak times 100 divided by 4.44 times A sub E, which we looked up, N, which we just calculated, and F is frequency in megahertz, which is 3.8. So we take the peak voltage in this case is 1250 times 100. That's 125000 in the numerator. In the denominator, we get 4.44 times the A sub E, which is 0.73 centimeters squared, times 37 turns, times 3.8 for 3.8 megahertz, we get 455.7. We divide that into E peak times 100, which is 125,000, and we get a peak flux of 274 Gauss, and at that point the core is disintegrated because there's not a chance. That's almost twice the flux density they can handle for that frequency. We might ought to be closer to 50 so that it could, in theory, survive being operated at 40 meters. So this core will fail it will fail horribly and it will stink the room up. So that is an example of exactly how to calculate this, given that we know the inductance. Another consideration is, will that number of turns fit on that core? For this example, it's a moot point because the thing will burn up. So for the core, we go to page 5, iron powder core size versus turns and wire size, and we assume perhaps an 18 gauge at the top, wire size 18. And we go down at the bottom of the screen to T-130, and a T130 core at 18 gauge can hold 51 turns total. That's considerably more than the 37 that we estimated by the formula. So why that's important is that that will leave some empty space on the core to use to mount the core against some surface without pressing against the windings. So, not a real difficult process, but a little confusing because it's all over this document. So that is it. So I have to go to a larger core. I'll look at the A sub L values. The T130, pardon me, 2 mix is 110. I'll probably go to a T184 at the bottom of the page here, which will have a sub L value of 240, which will bring the flux down considerably. And if that doesn't work, we keep going up in A sub L value. The next higher would be, oops, let's don't go that far out. The next higher for number 2 would be down here at the bottom of the page. That would be a T400A extra width. The A means a wide core. That would be an A sub L of 360. If that doesn't do it, then we've got to go to a different core material with a higher mu. So there it is from Amidons' technical document. Not a difficult process, but this is how we do it without guessing and probably getting it wrong and getting frustrated and giving up. So happy winding.